Howdy, how is everyone doing? Thanks for joining me today. In this video, I will discuss two important concepts in deep neural networks, which are very widely used in classification problems. These are the concepts of Softmax activation function and the related cross entropy loss. These two are typically used together for training a classifier in a neural network architecture. So everyone's excited? Let's get started. What is Softmax? Softmax is basically an activation function that is typically used in the last layer of the neural network to compute probabilities from real values. We will compare that with the more popular hardmax or argmax activation and discuss why Softmax makes more sense for training classifiers. Next, we will discuss the loss function that is used in conjunction with Softmax. This loss function is called Cross Entropy Loss. We will compare and contrast that loss with the more popular mean squared error. Understanding these concepts are pivotal to get a grasp on how deep neural networks work. This video is meant to clear the concepts of different things without getting into the coding part of things. In a follow-up video, I'll create structured coding tutorial on how to compute these metrics. Let us consider a canonical multi-layered perceptron for the classification problem. The input to this model is a three-dimensional vector x, shown on the left. The model is being trained to predict four classes A, B, C, and D, shown on your right. You can see those four classes are output of the last layer. These classes are mutually exclusive, so only one of will be true for a given sample. Typically, without any activation function which normalizes the output can be any real numbered value. In this case, the output for classes A, B, C, and D are 5.3, -2.8, 0.2, 1.5 respectively. These values are sometimes called logits. There are a couple of issues with such unbounded real numbers. First, how should we interpret them? Since these can be any real values, it is difficult to interpret them as confidence or probability scores. Further, unlike a probability distribution across a discrete set of outcomes, these values do not sum to 1. However, a straightforward way we can use them is by choosing the maximum value. In this case, the maximum value is 5.3, so we choose class A as the predicted class. Thus, we can set the output of class A to be 1 and everything else to be 0. This is more traditionally known as one-hot encoded vector, and the process of choosing the argument with the highest value is called argmax. Alternatively, this is also known as hardmax. Hard as in we just set the max value to 1 and ignore everything else. However, there is a major problem with the argmax function. It is not differentiable. That means argmax function may not be used by the gradient descent algorithm to find the correct weights and biases. Let us take a look at the reason why. This plot shows the logits on the horizontal x-axis and the activation on the y-axis. The dotted lines show the value of the argmax function. Remember how we said the argmax chooses the max value and sets that to 1 and everything else to 0. In this case, for anything larger than the second largest value, 1.5, argmax will output 1, which is shown by the red dotted line. And for everything else, it will output 0, which is shown by the yellow dotted line. So at the value of 1.5, there is a discontinuity in the loss function. Because of this discontinuity, the loss function is not differentiable. The derivative of the loss function with respect to the parameters is at the heart of the gradient descent algorithm. This is what drives the backpropagation based optimization algorithm. If the loss function is not differentiable, we can't use the gradient descent algorithm, thereby effectively stopping the training process. Hence, argmax is not a good choice for activation function. So what can we do then? Instead of choosing the hard max, we choose what is known as a softmax activation function. We need to force the output of the neural network to represent a probability distribution which is differentiable, and make sure that the 4 mutually exclusive probabilities sum up to 1. The way we do it is for every logit, we raise it to the power of e and then normalize the values across all such logits. So for instance, the softmax values for a represented as PA will be e to the a over e to the a plus e to the b plus e to the c plus e to the d, which in this case turns out to be 0.97. Similarly, the softmax of b, PB, will be e to the b over e to the a plus e to the b plus e to the c plus e to the d, which again results to 0.0003. The softmax of all the logits are shown here now. Note that they do sum to 1. Additionally, the softmax has a very nice representation for its derivatives. The derivative of softmax of A with respect to A is just the product of PA and 1 minus PA. Further, the derivative of PA with respect to B is negative of the product of PA and PB. Both of these are differentiable. So softmax is basically a soft continuous version of argmax. Unlike argmax, it is differentiable and can be used for gradient descent. Quick note, the computation of the derivatives are out of scope for this video. Now that we have learned why softmax is better suited for activation function for the last layer in a classification problem, let's see what loss function can be used to optimize such a model. Loss function is something that measures how far your predictions are from the desired output or the ground truths. It is also used to determine how well a model fits the training data. For the classification problem, the ground truth values can be either 0 or 1. And also, since these classes are mutually exclusive, there could be only one value. This is popularly known as one hot encoded vector, as mentioned before. For instance, ground truth for a sample could be 0, 1, 0, 0, which denotes that the sample belongs to the second class. A good prediction might be 0.2, 0.85, 0.08, and 0.05, which assigns probability of 0.85 to the second class correctly. And a bad prediction might be 0.2, 0.25, 0.35, and 0.2, where only 0.25 is assigned to the correct class. Mean squared error is a very popular loss function widely used in regression problems. It computes the square distance between prediction and ground truth. It is represented like the following formula. Now let us discuss what could be the potential issues for using mean squared error as loss function for training classification models. Let us take a look at an example. This is a plot that shows the graph of the predicted value on the x-axis versus the loss on the y-axis. The green line is the mean squared error for various predictions. The ground truth can possibly have only two values, 0 and 1. Let us consider the prediction for a sample where the ground truth is 1. Let's say the model behaves correctly and outputs a probability of 0.85 for the ground truth class. The prediction will be on the right side as shown with the check mark above. Now an important metric that we need to compute is the derivative of the loss function. This is at the heart of the gradient descent algorithm. As you can see, The gradient at this point of correct prediction is very small, almost zero, which is ideal since the prediction has almost converged to the truth and should not change much in the gradient descent process. However, if the model does a poor job, the prediction will be on the left, as shown with the cross above. So what will be the gradient of the loss function when the model does a poor job? The red line is a tangent, which shows the gradient of the loss function when the model does a poor job. Note that the slope of the tangent is not very large, which means the gradient is not very high. As discussed before, this gradient is important for the gradient descent algorithm. Since the gradient here is small, it might take a long time for the gradient descent algorithm to converge. Hence, mean squared error might not be the best for classification problems. So what loss function should we use then? In statistics, often to compare two probability distribution, we use a metric called cross entropy. Since the softmax outputs and the one-hot encoded ground truths are discrete probability distributions, which we can adopt the same metric here. The actual mathematical form of cross entropy for any two arbitrary probability distribution might be a little complex. It involves computing the summation of the product of the discrete values of one distribution and the log of the other distribution, as shown above. However, for classification problems, it becomes really simple. Remember, only one of the ground truth value is 1 and the rest is all 0. So cross entropy basically boils down to the negative log probability of the class where ground truth is 1, as shown above with minus log p of ground truth. Now the question is, does cross entropy behave any differently than mean square error? This is the graph which plots the predictions on the x-axis and the loss on the y-axis. The cross entropy values or negative log predictions are shown in the blue line. Let us consider a sample whose ground truth is 1. If the model generates a good prediction, say 0.8, the point will be on the right side of the line. The gradient is almost 0 here, as it should be. If the model has a bad prediction, say 0.2, it will be on the left side, as shown here with the cross mark. For a bad prediction, the slope is very steep, so the gradient descent will converge much faster. As you can see, the tangent here with the red line has a very large slope. That means the gradient is big too. Thus, we can see there are two major advantages of cross entropy loss over mean square error. First, when the predictions are bad, the slope of the loss function is much steeper for cross entropy loss. So, gradient descent will push the model towards the correct answer much faster. Secondly, it is much easier and faster to compute the negative log of one value versus the sum squared over all values. Hence, cross entropy loss is more desirable. Great. Let's summarize what we have learned here. So deep neural networks can have any arbitrary real values for output. We call these logits. For training classification models, we use Softmax to transform the logits to probability distributions. We compared the probability distribution with the one-hot encoded ground truth using cross entropy loss. During the model training process, we try to minimize this loss. During inference, you can choose the argmax if you just want the class with the maximum value. That's all. Thank you so much for taking part in my tutorial, and these are some of the references that I have looked into while creating these videos. Thank you so much.